So we can start the NT220 system by turning on the master power button, and we turn on the chiller button to power the thermal stage and cooling for that. It's water cooled up to 500 watts. We have our piezoelectric thermal chuck for the auto focus and alignment. We have our controller, which can provide the biasing and triggering. We have our send source, which can be used to select different LEDs and send the pulse to each of these LEDs, which we use for the measurement. And then we also have, for biasing, we have different options. There's a MCAD pulse ID system that can be used for high power. Right now we're going to be biasing a gallium nitride, a GaN device. Okay, let me start the software. We'll start Sanj V7. In the beginning, we need to set up our part. So we want to make sure that it's screwed in, mounted, secured into the stage. There's existing mounting holes, and you can make an adapter plate to make sure that you have good thermal contact with adding thermal paste, and also good mechanical contact, so it's not like kind of floating in the air. It's not going to be twisting when we're moving the stage around and when we have this thermal expansion from heating and cooling the stage. We'll make the electrical connections, and we have the bias to this part. And then we can, right now we're doing a GaN device, so we can put minus 2.1 volts on the gate to set it to the bias condition. We can select an LED, so we're selecting 365 nanometer wavelength, which is good for measuring the GaN semiconductor region. If you use visible light, then it's going to be transparent for the wide bandgap device. After that, we can then center the stage and enable the motion and select the magnification that we're going to be using for the system. So if you're just setting up your part initially, you can find your device, you can focus and align, and then you can rotate the turret to zoom into higher magnifications. And there's a fine focus on the right side and a coarse adjustment on the larger knob. Okay. There we go. Okay. And then you can do fine adjustments on this probe station below. Okay, so now we have it in focus. We turned on the power, so we apply power to the drain, and now we want to make sure that the current on this, okay, so we have like the correct current going through about 300 milliamps. And then after we know that our part is biased and connected, we can capture a reference image. So for this device, it's a GaN hemp, and we want to measure inside the channel region. So we can focus on the gate, and we can capture a reference region. So the gate is a thin region. We can capture a reference region over a little bit larger area to have higher, like a more unique image and higher accuracy for the alignment. And then after we're done with that, we can press start, and we now have we'll have our reference image over here. So from this reference region, let's just save again. You can put a file name in, ref demo. So this is the path, and here's the file name. We could press save. And now we can exit. And we can run, this is like the only manual parts that we would have. Then we can run an automated measurement after this. So from here, we can type in a file name of the part, 28 volts, 300 milliamps. We can select whether we want a calibration, a steady state measurement, or a transient measurement. And then we can also do the analysis. So we can, if you select the regions ahead of time, you can choose like what temperatures you want to measure, if you want to do inside the channel. We select where do we want to save this measurement. So we'll save it into this automated folder. And then for that reference file that we just measured, we can load that reference file so that it keeps everything aligned throughout this whole measurement. So it'll do an autofocus and auto alignment to make sure that everything is aligned down to fractions of a pixel. So once all of that is set up about how many measurements we want to do, then we can press start. And from here on, it would do an automated measurement where it's going to start off by doing the calibration. So it opens up the calibration software automatically. It will load in the reference region. So it's loading in this file name. Once it loads in that file name, you'll see the red region where it has that alignment region that we had saved before. So it will automatically focus, and then once we get in focus, you can see that everything is aligned to within 99%, a little bit more than 99%. And then it will start capturing data. So just for monitoring, like, it will adjust the filters in order to basically optimize and collect only the data that's like perfectly aligned. And at anything that's out of focus, if the system's moved or bumped, it will ignore that data, realign, and then capture the data again. If we relax these tolerances, then it'll capture data that's not 99% perfect, but 98% perfect. And it have a little bit more inaccuracies around these smaller features, but speeds up the measurement. So we also, for those reference regions that we just took, you can browse, and we did a scan demo. So if we choose the regions we want to measure beforehand, so we can select inside the channel. We can select off to the side, or we can select this channel over here. You can select up to 5 different regions. These will be the regions that we selected for these ROIs. The blue goes this number over here, so on. So once we have those, we can save the regions, and it will store those ROIs into the file so that we can like load them in if we come back to the measurement another day. So if you look at here, we can load in those same exact ROIs. So if we want to do like reprocess the data or choose like different regions. And since we selected these ahead of time, as it's running through the script, it will, once it's done doing the calibration and measurement, it will output the temperature for those regions. So after it's done capturing all those cold reference regions at the lower temperature, it sets the hot temperature up to 120 degrees. It'll refocus and realign everything, and then capture the high temperature data, and then that will be used as our calibration map. We have a thermal calibration map on the right-hand side. So we can use this one to get quantitative temperature data after we start biasing this part. So after we do the calibration, we have the stage return to 20 degrees temperature. And then it will continue on to the steady state measurement. It was done with the calibration. Now it's going to the steady state, so it's capturing a steady state thermal image, where again it loads in the reference image. It captures data with the part off, and then we'll turn the part on. And after it heats up, turns on, it'll capture data with it biased, and now we have an uncalibrated thermal image on this side. And it will repeat cycle a few times to reduce the noise. We have it's going to repeat 5 cycles for this measurement. So once this gets to 5, it'll save the file and continue. Okay, so now it's done 5 cycles. It will now save the data and then exit and continue on to the transient measurement. Okay, once it's done with that, it's going to start processing the data. So it saved it into this run 1. And from here, it'll load the calibration image. Okay, so it loads the calibration image. It will process each of these regions. It saves the data, and it's going to then load the steady state files. So it loaded the calibration image down here, image calibration map. And then now we have our calibrated thermal image on the right-hand side. So once all those things were kind of loaded in, we have our calibrated results with known temperatures. Okay, I think that's good. Okay, you can use the line profile to look at the peak temperature of these different regions. Okay, so that was all with thermoreflectance to get high spatial resolution. With thermoreflectance, we could change to infrared, where we select the infrared camera on this side. We typically do infrared measurements at 75C or 85C, and we rotate over to this infrared camera. So this camera is good for like lower magnification, just quick measurements to see the general profile. So this has 4.8 micron resolution per pixel. So if you're just looking at like kind of general heating, like where things are getting hot, this is the live image, this is like a differential image, and then you can turn on the part. This is turning on, not with 0 volts, but turning on a trigger that's connected to that. So now we have just a quick infrared measurement, but this is not emissivity corrected. But we can save this data. So here's our file name, and there's the path. And if we want to do the calibration, we do the same process. We go to the calibration, focus and capture, and then press start. 75C. A little bit faster, yeah. Either way, like no matter what thermal imaging technique, you still have to change the stage temperature to some known points. So you'd have to do this with infrared, with thermoreflectance, with any thermal measurement. You have to have known temperatures, and that's why we have a thermal stage with a known temperature. We calibrate between two known temperature regions, and then we can press save. So once the temperature is stabilized, then we will capture more calibration images. So it's acquiring the hot images. Once we capture enough of them, then we'll save the data. Okay, so now that's our infrared calibration image. And we can load our IR calibration with the IR image. And now we have a calibrated infrared image. Okay, and we can draw our line profiles as well. So the infrared's good for like looking at the whole chip and lower magnification quickly, but the resolution is not going to be able to give you like true peak temperatures inside the channel.